5 centuries, 500 decades, and 5,000 years since humanity started asking questions about our universe, and we've successfully raised more questions than we can actually give an answer to. Today, there's only a handful of these questions that have actually been answered compared to the millions or even billions of unanswered questions seeking a conclusive answer to why, what, when, how. We were able to establish the existence of black holes and the fact that they are born from the deaths of dying stars. We also discovered that the universe was created as the result of a singular cosmic explosion, the Big Bang, and that the universe as we know it is about 13.8 billion years old. But what we don't know is what actually happens inside a black hole, or what was there before the Big Bang, or why is space always dark given the infinite number of stars in it? There's more. For decades, scientists have attempted to provide solutions to these paradoxes, but only end up fabricating theories that can't conclusively answer them. Today, we explore the most striking of these paradoxes and seek for their solutions. Let's delve right in, shall we? Have you ever wondered why the night sky is always dark? I mean, we have an infinite number of sun-looking stars and even larger, but still, there is darkness. German astronomer Heinrich Wilhelm Olbers, who discussed it in the early 19th century, revolves around the apparent contradiction between the darkness of the night sky and the assumption of an infinite, eternal, and unchanging universe filled with an infinite number of stars. The paradox starts with the idea that if the universe is infinite, static, and filled uniformly with stars, then in any line of sight from Earth, eventually, your line of sight should intersect with a star. Considering an infinite number of stars spread throughout an infinite universe, one might expect that the night sky would be as bright as the surface of a star. However, the night sky appears dark, with only a limited number of visible stars and celestial objects. This paradox raises the question: why isn't the night sky uniformly bright if there are an infinite number of stars? Several proposed explanations have been suggested to resolve Olbers' paradox. The finite observable universe. One solution posits that the observable universe is finite. Even though the universe might be infinite, our ability to see it is limited due to the finite speed of light and the age of the universe. Light from very distant stars might not have reached us yet, or it might have traveled beyond the visible horizon. Redshift and expanding universe. The expansion of the universe causes the light from distant stars to redshift. Stars' light moves away from us, stretching it to longer wavelengths, and this redshift can move the light beyond the visible spectrum, making those stars undetectable to the human eye. Dust and absorption. Interstellar dust and gas could absorb or scatter light from distant stars, reducing their brightness before it reaches us. This absorption could account for the darkness of the night sky. Unseen or dark objects. Hypothetical objects such as dark matter, black holes, or other undetectable entities could exist and might contribute to the darkness of the night sky. While these proposed explanations aim to address Olbers' paradox, it remains an essential concept in cosmology, emphasizing the complexities and mysteries surrounding our understanding of the universe's size, age, composition, and structure. Modern astronomical observations and theories have provided substantial insights, but the paradox continues to stimulate scientific inquiry and curiosity about the nature of the cosmos. Cannot be created or destroyed. The paradox of the black hole information, also known as the black hole information paradox, stems from the conflict between classical physics, particularly Einstein's general theory of relativity, and quantum mechanics. This paradox delves into the fate of information that falls into a black hole. In classical physics, black holes are described as regions in space where gravity is so intense that not even light can escape their grasp. According to general relativity, when matter falls into a black hole, it reaches the singularity, a point of infinite density where all information about that matter is seemingly lost from the observable universe. Quantum mechanics, on the other hand, states that information cannot be destroyed. It insists on the principle of unitarity, which means that information about a system is conserved over time. This concept implies that if you know the complete state of a system at one point in time, you should be able to predict its state at any other point in time. The conflict arises when considering what happens to information that falls into a black hole. If a particle or any form of information enters a black hole and is seemingly lost forever as it reaches the singularity, it violates the principles of quantum mechanics, which suggests that information should be conserved. Physicist Stephen Hawking famously proposed in the 1970s that black holes can emit thermal radiation, known as Hawking radiation, due to quantum effects near the event horizon. This radiation implies that black holes can slowly lose mass and eventually evaporate entirely, seemingly carrying away information about what fell into them. However, this raises a crucial question. If a black hole completely evaporates and disappears, does the information that fell into it also disappear, violating the principles of quantum mechanics? Several proposed solutions and hypotheses have been suggested to resolve this paradox. Let's take a look at some of them. Holographic principle. This idea posits that all information about what falls into a black hole is encoded on the black hole's event horizon. The information remains preserved, but in a highly scrambled or holographic form on the two-dimensional surface of the event horizon. Firewall hypothesis. Some physicists propose the existence of a firewall near the event horizon of a black hole, which would destroy any information entering the black hole, thus maintaining consistency with quantum mechanics. Black hole complementarity. This concept suggests that different observers, such as an observer falling into a black hole and an observer outside, would perceive different realities due to the effects of quantum mechanics and general relativity. For the time being, if you fall into a black hole, you'd completely lose your meaning and cease to exist. But there's more. Check out my video on what happens inside a black hole. Is motion real or just an illusion? Zeno's paradox of motion. This is a philosophical puzzle proposed by the ancient Greek philosopher Zeno of Elea. It's a series of paradoxes aimed at challenging the concept of motion and the divisibility of time and space. The paradox centers around the idea that in any given instant of time, an arrow in motion is not moving as it occupies a single position at that precise moment. Therefore, at each individual instant, it seems as though the arrow is at rest, rather than in motion. Zeno argued that if time is composed of a series of these instants, and an object at each instant appears to be motionless, then motion itself becomes an illusion. He used this paradox to argue that change and movement in the physical world are impossible or paradoxical. However, modern mathematics and physics have provided various ways to resolve or understand Zeno's arrow paradox, continuity, and infinitesimal calculus. Mathematicians developed the concept of infinitesimal calculus to deal with the idea of motion and change in infinitesimally small time intervals. It involves considering the sum of an infinite number of infinitesimal changes to represent continuous motion. Understanding limits. In calculus and mathematical analysis, the concept of limits allows for the consideration of motion and change over infinitesimal intervals without denying the possibility of motion. This mathematical tool reconciles Zeno's paradox by enabling the understanding of how motion can occur despite being composed of discrete, infinitely small intervals. Modern physics. Quantum mechanics and relativity in modern physics have altered our understanding of space and time. They introduce the concept of space-time as a continuum rather than a series of discrete moments. According to these theories, space and time are intertwined, and motion can occur smoothly in this four-dimensional space-time framework. The arrow paradox highlights the philosophical conundrum between our intuitive perception of motion and the mathematical and scientific understanding of motion in a continuous and interconnected universe. While it remains a fascinating thought experiment, advancements in mathematics and physics have provided frameworks to explain how motion is possible despite Zeno's apparent paradoxes. The paradox of determinism and free will explores the apparent conflict between two fundamental concepts: determinism and free will. What are determinism and free will? Determinism suggests that every event or state of affairs, including human actions and choices, is determined by preceding events or conditions in a causal chain. In contrast, free will implies that individuals have the capacity to make choices and decisions that are not wholly determined by prior causes. The paradox arises when considering whether these concepts can actually coexist. Determinism holds that the state of the universe at any given the connection to human decision-making remains speculative. Challenges to moral responsibility. The debate surrounding determinism and free will has implications for moral responsibility and accountability. If our actions are entirely determined by prior causes, it raises questions about whether individuals can be held morally responsible for their actions. The paradox of determinism and free will remains a profound philosophical and scientific debate that touches on the nature of human agency, moral responsibility, and the fundamental fabric of the universe. Resolving this paradox involves grappling with the intricate relationship between causality, determinism, freedom, and the nature of human decision-making. Now on to something more peculiar. Are we alone? The Fermi paradox, named after physicist Enrico Fermi, encapsulates the apparent contradiction between the high probability of the existence of extraterrestrial civilizations in the universe and the lack of evidence or contact with such civilizations. It prompts the question, where is everybody? This paradox originates from the following observations and reasoning: scale of the universe and probability of life. The observable universe is vast, containing billions of galaxies, each potentially hosting billions of stars with planets. Considering the sheer number of potentially habitable planets in the universe, the likelihood of life emerging elsewhere seems plausible. And also, the potential for technologically advanced civilizations, given the age of the universe and the potential for habitable conditions on other planets. It's reasonable to assume that some extraterrestrial civilizations could have evolved technologically far beyond humanity. Despite these probabilities, there's a conspicuous absence of direct evidence or contact with advanced extraterrestrial civilizations. Several hypotheses attempt to explain this paradox. Rare Earth hypothesis. This hypothesis posits that the conditions necessary for complex life are exceedingly rare. Factors such as a planet's location in the habitable zone, plate tectonics, a stable atmosphere, and a large moon for stability may be rare, limiting the emergence of life. Fermi's Great Filter. Theory. Fermi suggested that there might be a great filter, a barrier that significantly reduces the chances of life evolving into advanced civilizations. This filter could be a critical step in the process of life emerging, or a hurdle civilizations face that prevents their expansion and visibility in the cosmos. If the Great Filter lies ahead of humanity, it raises concerns about our future survival. Technological singularities and transcendence. Some speculate that advanced civilizations may reach a technological singularity where they transcend traditional forms of communication or existence, making them undetectable by conventional means. Galactic Zoo hypothesis. This conjecture suggests that advanced civilizations deliberately avoid contact with emerging civilizations like humanity to allow them to develop naturally without interference. The Fermi paradox continues to inspire discussions and exploration in fields such as astronomy, astrobiology, and philosophy. It challenges our assumptions about life in the universe, the potential for advanced civilizations, and the implications for humanity's place in the cosmos. The bootstrap paradox is a fascinating concept within the realm of time travel and causality, proposing a situation where an object, information, or event exists without a clear origin, leading to a loop of cause and effect with no discernible beginning. Named after the phrase, pulling oneself up by the bootstraps. This paradox involves a cycle of events that seem to create themselves with no identifiable original source. Suppose a person travels back in time and delivers a famous manuscript, let's say a renowned novel, to a famous author before the author has written it. The author publishes the novel, and it becomes immensely popular. Subsequently, the book is passed down through generations, and eventually, someone finds it, reproduces it, and travels back in time to deliver it to the original author. This creates a loop where the manuscript's origin becomes unclear. Did it originate from the author? Or was it brought from the future by a time traveler? In essence, the information, or object, or event appears to be self-created within this closed loop of cause and effect, without a true point of origin. It raises questions about causality, the nature of time, and the continuity of events. Well, several theories and potential resolutions attempt to address the bootstrap paradox. Let's take a look at some of them. Multiverse theory. Some interpretations of time travel suggest that when someone travels back in time and changes events, they create a new branch or timeline in a parallel universe. In this scenario, the object or information from the future might loop back in time, but it doesn't create a paradox within the traveler's original timeline. Stable time loop or predestination paradox. This perspective posits that events are predetermined, and that time travelers were always meant to go back and ensure the loop happens. It implies that the origin of the object or information is inherently tied to the loop itself, without an external cause. Multiple iterations or iterative creation. The object or information might have been created, lost, and recreated multiple times in the loop, with each iteration contributing to its existence without an original creation event. The bootstrap paradox challenges our understanding of causality and the idea of a linear cause and effect relationship. It invites contemplation about the nature of time, the possibility of closed loops in time travel, and the potential implications of information existing without a clear origin, creating a fascinating conundrum within the framework of time manipulation and paradoxes. Questions, paradoxes, theories, but no answers. This is where I will end this video. Like, subscribe, share your thoughts down in the comments, and I'll see you in my next video.